In this video, we're continuing the explanation on the principles behind these work problems. And so in the first video, we saw that work is force times distance. And this is a nice, easy formula to use if your force is constant. But as you probably will have guessed, in a college-level calculus class, the problems are not going to be quite that easy. So we're going to look at problems where the force is changing with the variable x. So instead of a constant force, you have a force function. So your force is changing. So imagine that you're pushing, pulling, dragging, carrying an object across this interval AB. If the force acting on that object is constant, then you would simply use the force times distance formula, multiply the force times b minus a. However, as I indicated, the problems are not going to be quite that easy. Now imagine as you're carrying, dragging, pushing, pulling across this interval, your force is changing for whatever reason. Perhaps you're carrying something with a hole in it and something is leaking out as you're carrying it and it's getting lighter and the force is decreasing. So what does the work accomplish there? If you took the maximum force and multiplied by the length of the interval, that would give you an upper bound for the work. It would be an overestimation. So how do we get the true work required? Well, we look at this interval, we chop it up into pieces, we'll pick a representative point, x sub I star, calculate the force function at that point, and we're going to consider that to be the force over this small interval. Now that's not the true force because the force is changing. It's not the true force necessarily. But we'll assume that it is. And take that force and multiply by this interval here, the length of this interval, which is delta sub I. And we'll use that as an estimation for the work done over that small subinterval. And to make things a little bit nicer, let's choose the right endpoint of each subinterval, and let's choose our delta I to be b minus a divided by n. In other words, we're going to chop the interval AB into n smaller subintervals of equal length. So we calculate the force function of the right endpoint, which is a plus b minus a multiplied by I over n, and then we'll multiply by the length of the small subinterval. This is an estimation of the work. See, this is approximately the work. So what is the work done? Well, we'll take the limit as n goes to infinity of this summation. That is also the same as saying we're going to take the limit as the delta i's go to 0. But we're going to take more and more subintervals. We'll take the limit as the number of intervals goes to infinity, calculating the force function at the right endpoint, multiplied by the length of each interval. And we recognize this as an integral. If f is continuous, it's integrable, and so this is the integral. And so we're going to use integrals to calculate work. What we're going to do is we're going to integrate, as x ranges from a to b, we're going to integrate the force function. The hard part of the problems in this chapter is figuring out what f of x is. Once you figure out what f of x is, usually calculating the integral is not the hard part. In the fourth video, when we look at a water pumping problem, we'll actually set it up like this and recognize it as an integral. But most of the time we're going to integrate the force function. But in the fourth video we'll do it a little bit differently.